but whenever there is an equality, whenever the constraints are in the form of an equality, we can use that one to solve the problem neatly. Okay, Lagrange multiplier method can be used. Okay. So let me illustration with a very simple example. What is the idea? Let's say we want to extremize a function. I'll always like to write the constraint in this particular. It's a very simple example. Okay, you don't need Lagrange multipliers to solve it, but the whole idea is that you get to know about the basic principle of Lagrange multiplier this way. Supposing you are asked to find this problem, okay, you don't have to draw any picture, nothing is required. You will say that the constraint, okay, the equation 2, the constraint implies y is equal to L minus x. So then this function together with the constraints y of f of x, that is what we have to extremize. We now have only one independent variable, right? After using the constraint to eliminate y, we have reduced the degrees of freedom to 1. So we got a new function f of x, y of x. I'll call this one as some new function, some f tilde of x. It's a new function of one variable. So in this example is simply x square plus L minus x the whole square. So this becomes 2x square plus L square. Okay, many ways of handling it, but I again like to think in this way, because completing squares is always a good idea. So this I will say is like x minus L by 2 the whole square minus L square by 4 plus L square. What I am doing is just completing the square. So x square minus Lx, I'll write as x minus L by 2 the whole square minus L square by 4. So that x square minus Lx plus L square by 4 minus L square by 4. So this function is nothing but 2 times x minus L by 2 the whole square plus L square by 2. It's a positive definite function. So if you make a plot of that one, it will look like this. If L is positive, it will be something like this. This will be, this is your x, this is your f tilde, and this value is simply L square by 2. So clearly you can see that there is a minimum at L by 2. If L is negative, it will be on this side, that's all. Okay. So nothing to prove there. Of course, if you start with this function, set it to find the derivative of this one, that is analytic method. You can say that at extrema, okay, let's say x equal to some x star, df by dx must be equal to 0. So when you do that, you find 4 times this one minus L equal to 0, which means x star is L by 2. Same result. Take the second derivative, you would find the second derivative is 4, which is positive, so the function is a minimum. Okay. You can use both ways. You don't have to all the time use differentiation. You can just many times completing squares, etc. would help. Okay. But this is not what we want to do. Okay. This is just to have a reference point. So if x is L by 2, then what is the value of y at that point? L minus x. That is also L by 2. So there is a unique point, unique extremum here, which correspond to a minimum. Okay. So the answer that we have obtained by analytic methods is there is a minimum at L by 2, L by 2. Both x and y equal to L by 2, you have got a minimum. That's what we found. Now to get a general principle, let us look at this problem graphically. So we have a constraint. Let L be positive. So the constraint is x plus y minus L equal to 0. That means y is equal to L minus x. So there is a straight line like this. This is the constraint. X plus y minus L equal to 0. So when L changes, this line would get shifted parallelly. When L is increased, you get parallel lines to the top of this, and when L is decreased, it is like this. Along the line, x plus y is a constant. So changes always take place perpendicular to the constraint. Okay, that is something which I have to realize. So only if you travel normally, then only the change occurs. Along the horizontal, the constraint is maintained. Okay? So change takes place in the direction of the gradient of f. So change in f, or this is the constraint, right? Change in g takes place in the direction of gradient of g. This is true not only for 2 dimensions, whatever be the case. If it is 3 dimension, you will have a constrained surface. Again, the change would occur normal to that. Okay? So that's a very general idea, gradient. Now, our function here, f, that is of this form. If x square plus y square is small, it's a circle. So if the radius is small, it doesn't intersect with the constraint. So you don't get the solution corresponding to that. So you have to go on again increasing the value of x square plus y square. So each circle corresponds to one single value for the function f. This corresponds to, for example, let's say x square plus y square equal to some radius r1. This corresponds to x square plus y square equal to r2, etc. So along each curve, the value of the function is a constant. Again, you have to go along the direction normal to that, along the direction of the gradient for f to change. Okay. So f also changes in the direction of the gradient. Its gradient of f. So ultimately, when you go on increasing the radius here, there will come a stage when it will be just tangential to that. When you increase the value of f further, it cuts into 2 places. Right? So now the question is, what is the value, the extremal value of our function f subject to the constraint? That happens when the function is exactly tangential to this particular one. This what you saw earlier also. Remember, when we eliminated the variable, what did we get here? When both of them were combined, we had 2 times x minus L by 2 the whole square plus L square by 2 here. The minimum occurred when x is equal to L by 2. Exactly when it is tangential to that. But there is only one solution, not 2 solutions. So that means now, this analysis shows that for the extremum of f, okay, you should find gradient of f should be parallel to gradient of g. At that point, at the extremal point, the gradient of f and gradient of g should be parallel to each other. That means gradient of f equal to some constant times gradient of g at the extremal point. Lambda is a constant. This is the central idea there. How is it implemented here? So you say this is the function that we have to extremize. There is a constraint like this. Now it says consider a new function. Okay. let's say some function psi of x, y, and one more variable lambda, which is equal to f of x, y, the function that we want to extremize. Minus or plus doesn't matter, but I am used to putting it as a minus sign here, g of x, y. Let us consider a function like this. Brief discussion about that one. This is a function that we want to extremize. This is the constraint. When the constraint is satisfied, g is 0. That means for those values of x, y consistent with the constraint, this is actually the f itself. We are not considering any new function. It is the same function. Okay? But for other values of x and y, this is different. But our aim is to enforce the constraint all the time. Okay? That means ultimately, when I consider a function like this also, I am actually considering this one. Okay? But some extra leverage is there. Now if you look at this, of course, it now becomes a function of three variables, x, y, and the Lagrange multiplier. Whereas when we eliminated the y, we had only one variable. So we have increased the number of degrees of freedom here, but nevertheless, we have something like this here. Now we say that we have to extremize this function of three variables. So how do we do that? We have to set the derivative of this function with respect to all the three variables to 0. This is what we have to do. So we demand or enforce this d psi by dx equal to 0. When you do that one, you get df by dx minus lambda times dg by dx equal to 0. That's what it will be, right? And demand d psi by dy equal to 0. This corresponds to df by dy minus lambda times dg by dy equal to 0. And you can see these two together is nothing but gradient of f is equal to lambda times gradient of g. Of course, we have one more, that is d psi by d lambda equal to 0. So that means g of xy equal to 0. This is a constraint. That means we are going to have simultaneous solution of all these three equations. So while solving, we are going to enforce that the constraint is satisfied. So we are extremizing the original problem. This is the central idea, not only for this problem. Every problem involving one or more constraints of the type that I have done, equality constraints. Okay, you can use this particular method. Okay. So first one will give you 2x minus lambda equal to 0, 2y minus lambda equal to 0, and then you have x plus y minus L equal to 0. So this tells that both x and y are equal. Lambda is equal to that quantity, and if x and y are equal, each one of them is equal to L by 2. So this leads to, I would say, at the equilibrium value, right? At the so x star, y star, this is equal to L by 2, L by 2. That's what you get. Of course, here now you have to also find out a rule for finding out what is the nature of the extremum if you use this one. Okay. So here the way to describe it will be like this. Okay. The nature of extrema. So what you have to do is, the name of that particular quantity I am going to talk is called Hessian. It is actually this quantity, the matrix of dx squared, this one, d squared psi by dx square, dx dy, that of course evaluate at that extremal point. The second derivative matrix, In the context of one variable problem, you take the second derivative. When you take the two variable or multivariable problem, you will have second derivatives with respect to each one of the independent variables and mixed partial derivatives also. So this particular matrix is called the Hessian. Okay? Hessian. This must be positive definite. What it means is that its eigenvalues should be positive. All the eigenvalues. That is the requirement. In this case, of course, you can see it's a very, very simple thing. Your psi is given by x square plus y square minus lambda times x plus y minus L. So when you take the second derivative with respect to x, you get 2. There is no xy term, so it becomes 0. And y square is there, that gives you 2. So you see that both the eigenvalues are positive. That means it corresponds to a minimum. This is for a minimum, for the extremum to be a minimum. I will not say must be, I will say if it must be positive, positive definite for x star, y star to be a minimum. If it is negative definite, all the eigenvalues are negative, it would correspond to maximum. Whatever we say with respect to second derivative for a single function, now do corresponding things for the Hessian matrix there. Positive definite, negative definite. If the eigenvalues are of mixed character, then of course you have saddle. You can make it a little bit more complicated and see the power of it by just inverting the role of f and g. Now let us consider extremize a function x plus y with constraint g of xy equal to, just interchange the role of the two. Okay. So the constraint is the circle. So this is the circle x square plus y square equal to a square. Now our function is x plus y. So when the value of x plus y changes, we get different curves like this. Right? Like this. So you see that there will be one line here which is tangential here. In that case x plus y, because it is in the first quadrant, it is positive. Here it is in the third quadrant, x and y are negative. It is symmetric. So this would correspond to a maximum and this would correspond to a minimum. You find same problem now when you interchange, you got variety. You get a maximum as well as a minimum in this one. Okay. We can solve it by the direct method as well as with the Lagrange multiplier. This time I will solve first with the Lagrange multiplier. Okay. So our function psi is given by x plus y minus lambda times. So this is the function, the augmented function that we consider. That is augmenting the function f with the constraint g. A new function is constructed which would be identical to the original function f when constraint is satisfied, but otherwise it's different. Okay. So we consider this function. So what is our rule? At the extrema, derivative of this with respect to x, y and lambda should be equal to 0. So d psi by dx, d psi by dy and d psi by d lambda, all of them have to be equal to 0. So the first one, d psi by dx, this will give a 1 minus 2 lambda x equal to 0. Next one, d psi by dy, 1 minus 2 lambda into y equal to 0. Third one, of course, x square plus y square minus a square equal to 0. Looking at it is obvious that x must be equal to y. So we can put at the that will denote by the symbol x star and y star the extremal point. Okay, we have to re-emphasize that one. We are looking for those values of x and y for which these conditions are satisfied. They are not satisfied for all values of x, y. Okay, so those values we are denoting. So this equation very clearly tells that x star equal to y star. Nothing to do basically. Substitute that here. So these two imply x star equal to y star. So this equation then implies 2 times x star square equal to 2 times y star square equal to a square. So you have x star equal to a square by 2 plus or minus. Okay. So you have two solutions here. X star y star equal to a by root 2 into 1 1. Other is minus a by root 2 into 1 1. So this corresponds to an extremal value x plus y equal to root 2a, and this corresponds to minus root 2a. Maximum, minimum. So this point corresponds to a maximum, and this corresponds to a minimum. Let us see with our Hessian. Any question? Was there any question? No. All right. So let's look at this one here. We have to put in. Many times we will denote by this symbol. This also is good to learn. If you put in something like this, basically this stands for second derivative with respect to x, second derivative with respect to x and y and so on. Okay, it's good to know the notation. So this will be equal to, this is the Hessian. Second derivative with respect to x. So you'll get minus 2 lambda here, and here you'll get minus 2 lambda, and of course 0 here. Now, what is lambda equal to? Minus 2 lambda is minus 1 by x star. 2 lambda x star equal to 1. 2 lambda x star equal to 1. So 2 lambda is 1 by x star. So minus 2 lambda is minus 1 by x star. So minus 1 by x star, minus 1 by x star, 0, 0. Here both x star and y star are, x star is positive. So these two eigenvalues are negative. So you get a maximum. Whereas for this one, x star is negative. So minus 1 by x star here is positive. Obviously that corresponds to a minimum here. You see the amount of work involved is only that much. You solve it very easily. Okay. This is something which you can solve with the direct method also, but you will have extra work to do. Let me show you that. So we have this, the constraint. Is x square plus y square equal to a square. So this implies two possibilities. One is y equal to plus square root of a square minus x square, and other is minus square root of a square minus x square, which means in this case y is positive and in this case y is negative. That is, if you find that during the intermediate stages of the calculation you have multiple possibilities, you must pay attention to this particular fact that y, having chosen y to be like this, the solution you are going to get also must be consistent with that. So I will say this is possibility 1 and this is possibility 2. So what is the idea of doing that one? Basically to eliminate one of the variables using the constraint. Okay? Because the constraint is nonlinear, we had multiple possibilities. In this case, 2 possibilities. So we have to use each one of them. So when the first possibility is used, a new function f of x, y of x, this is what I was denoting by the symbol f tilde of x here. This becomes x plus square root of a square minus x square. So this is a function that we have to extremize. When we use the other possibility, it will be x minus square root of a square minus x square that you have to optimize. Okay. Let's try to handle this one. So try to locate the extremum. That is done by demanding the derivative of this equal to 0 at the extremal point, and that gives you simply 1 minus x divided by of course put a star here. So this of course tells that x star equal to square root of a square minus x star square. This must be positive because this square root is positive square root, so x star must be positive. But how to get the value? That is done by squaring it first. So you square it, you get x star square equal to a square minus x star square. So this gives you x star square equal to a square by 2. This may give an impression that you get two solutions, plus or minus a by square root of 2, but you should choose only the positive square root. Then of course y is also given by the same value, you get back the solution. But this much of care is required in solving it. Now for the second branch, similarly do it. So only accept only x star equal to plus a by root 2 in this. When you look at the other possibility, put a minus sign, you get the same thing, but in this case you have to choose the option minus a by root 2. Solution will be identical. So which is simpler? I just want to get some feedback from the students. Are you able to follow what I am saying? Lagrange multiplier methods. Are there students here? Nobody is responding. Yeah. Are you following what I am doing here? Yes? No, because we have to know whether this method or we have to still think of simpler methods of teaching. Okay, so that's why some feedback is required. But I thought it is very simple. Because many times people use Lagrange multipliers mechanically and land up in trouble because at some point some mistakes would be made. But once you realize the basics, it becomes so simple. We'll come to that after this. Okay, let's first finish this.